So here you say, so injection. Okay, injection. So for any x, so for any fx, comma, okay, better idea. If fx equals fy, then x equals y. It says for any two elements here, if they are equal, then they have to map, then the two things have to be different. So if this thing is the same thing as this thing itself, then this thing has to be the same thing as this thing. We cannot have two elements here be the same, such that two elements here, the thing that's mapped to it, is also the same. There. Okay. So that's his definition of bijection. Okay, examples. The first part. I'll keep those. So first example, we have a bijection between, so there is a bijection between z and z, or z plus and z minus, the positive integers and the negative integers. What can we do? Well, let's look at the function f of x equals negative x. Right, guys? Blue is better. So, okay, check the first property. Okay, first we prove surjection. All right. So let's prove the first property. Let x be in z minus. Then minus x is in z plus. Right, guys? Multiply by minus 1, then z plus, right? So f of minus x equals minus x. By definition, equals x. Since x was arbitrary, x could have been anything, and this is true for arbitrary x, then it's true for all x. Therefore, since x was arbitrary, it could have been any number, which is the variable. F is a surjection. Okay. Good. Next part. Okay. I prove its surjection. Now I prove its injection. Let's, okay. Right? F of x equals f of y. Then by definition of f of x, right? Trying to prove this bijection. Then minus x equals minus y. But then multiply both sides by minus 1. It gives you x equals y. Good. Okay. Therefore, f, since it fulfills both properties, f is a bijection. This function, f of x equals minus x. A bijection from positive integers to negative integers. So that's this first example. Let us do a little bit harder example, but we should always consider the cheap finite case. So cheap finite case we do right now. Okay. It doesn't have to be pretty like that. It could be just, if it was finite, it could be direct manipulation. So let's consider the dihedral group. Let's consider the dihedral group of order 4 is equal to set E, comma R. Do you see this there? Yes. Comma R, comma R squared, or S, yeah, comma S R. Good. Dihedral group of order 4. Okay. So I say there is a bijection between D4 and 1 and 1, 2, set 1, 2, 3, 4. Okay, I'm going to erase this because you guys should know it by now. If not, always a why. That is why it's on YouTube. Okay, so let's do a definition. Okay, so proof, very simple, very simple proof. And then after this, because I don't want anyone online thinking I'm dumb, I do really good proof. Actually, one after this. Proof. Let okay, now we're going to define that. Equals, okay. So in preschool, you have 4 toys. You're counting, you go to market, okay? You have 10 tomatoes. You call one tomato, tomato 1, next tomato, tomato 2, so forth, up to tomato 10. I do the same thing. If f of x, I'm going to say equals to 1, if x equals e. R, or 2, if x equals r. 3, if x equals s. And 4, if x equals sr. Okay. So, okay. It is first a bijection. Well, it's a bijection. It's first surjection. Why is it surjection? Because first check, is something being mapped to 1? Yes. X is being mapped to 1. So 1, so something being mapped to 2. When you have finite group, you can actually do this. Very quick counting. Something being mapped to 2, 2, good. Something being mapped to 3, so 3, x equals s, maps to 3, yes. Something being mapped to 4, yes. You know, you cannot do this for every case. This, for example, you're dealing with integers or natural numbers, you cannot do this trick. Remember, just because one ninja like ramen does not mean all ninjas like ramen. You've got to either prove it for arbitrary case or use induction in that case when you're dealing with that. And if you're dealing with a finite group, you can do this trick, but it's not as pretty. But when you have a small group like this, or not, a small set like this, I should talk about this. I'm going to talk about this. Okay, surjection. Secondly, induction. Very simple. No two elements are mapped to the same. There, 10 seconds. Is anything mapped? Anything here? Two things are the same, being mapped to two same elements? No. Then this is obviously this is easily injected. So I just proved there's a bijection. Okay, let's do two more examples. One small example, then one big example. Okay. So small example, one more. Well, this is medium-sized example. Okay. So consider the function f of x equals e to x, and we're dealing with the function from the real numbers to the positive reals. Okay. For example, pi will be here, but negative pi will not be here. It'll be here, but it will not be here. Okay, so first thing, I prove this is a bijection. Okay, first let's check surjection. Okay, so let's x be in R class. Well, remember that natural log